Hey, welcome back. So today I am going to answer one question, and by the end of this video you will never get confused again. That question is, what is the actual difference between a list and a tuple in Python? Not just the boring one is mutable, one is not answer you get on Stack Overflow.
I am talking about how fast is each one. What does Python do under the hood when it sees a list versus a tuple? What does the bytecode look like? Why does Python even have both? And we are going to use real tools, time IT, this, and compile to see the difference, not just hear about it.
Think of a list like a shopping bag. You can put things in, take things out, change your mind, add more stuff, or throw things away. A list is mutable. That means you can change it.
Now think of a tuple like a sealed box. Once it's packed and sealed, it's done. No adding, no removing, no changing. A tuple is immutable, meaning you cannot change it once it's created. Okay, but why would I ever want something I can't change? Great question. Keep watching. We are going to answer that with proof. Now, let's prove that tuples are faster. We are going to use Python's built-in library timeit module. This tool runs a piece of code thousands of times and tells you exactly how long it takes. We import timeit module. It's already inside Python. No installation needed. Just import and use. Simple. Now look at this carefully. Timeit.timeit method takes two things. First, the code you want to test written as a string in quotes. So 1, 2, 3, 4, 5. That's just a list written as a string. Timeit will execute it as actual Python code. Second, number equal 10 millions. That's how many times to run it. The underscore is just Python's way of writing big numbers. When it's done, it returns the total time in seconds and we store in list of time. Now, third line, exact same thing, but now we are timing a tuple. Same five numbers, same 10 millions runs. Notice the only difference is square brackets versus round brackets. That one tiny change and the result is going to shock you. Now we print the results. That colon dot 4f inside the curly braces just means so 4 decimal places because these numbers are small like 0.4821 and we want to say them clearly.
This is the fun one. We divide list underscore time by tuple underscore time. If list took 0.48 seconds and the tuple took 0.06 seconds, dividing them gives us 8, meaning the tuple was 8 times faster. Colon dot 2f means so 2 decimal places. So it prints something like 8.2x faster. Now let's run the code. Wait, did you see that? A tuple was created 8 times faster than a list. Why? Because Python is smart. When it sees a tuple with fixed values called a constant tuple, it does not build it fresh every single time your code runs. It pre-bits it and keeps it ready. A list. A Python has to build it fresh every single time because remember, list can change. So Python can never assume, oh, same list as before. Okay, so in the last part, we proved tuples are 8x faster to create. But here is a question nobody asked. What about reading from them? What about accessing elements? Is a tuple faster at that too? Or does the list fight back? Let's find out right now. Now, before we look at the code, notice something. Last time, timeIT took just two arguments, the code string and the number. This time, it takes three. There is a new one called setup. And that setup argument is the whole reason this test works correctly. Let me explain why. Look at the STMT first. That's a short for statement. It's the code we actually want to time. In this case, x equal to my list of 2. Grab the element at index 2 from the list. But wait, my list has to exist before we can read it from. That's where setup comes in. Setup runs once, just once, before the 10 million test runs begin. It sets up whatever your code needs. So here it's create the list. My list equal to 1, 2, 3, 4, 5. Then timeIT runs stmt 10 million times, and then the setup time is not counted in the result. Only the stmt time is measured. This is really important. Without setup, we had have to put the list creation inside stmt, and then we had be timing the creation again, not just the access. That would be unfair. Setup keeps the test clean and honest. Identical structure, just tuple this time. Setup creates the tuple once, stmt reads from it 10 million times. Clean comparison. Let's run the code. Okay, so both are roughly same. The tuple is slightly faster, maybe 10%, maybe less, but nothing dramatic. Not the 8x we saw before. Both list and tuples store their elements the same way internally, as a row of slots in memory, numbered from 0. Index 0 here, index 1 here, index 2 here, like numbered boxes in a row. When you say my list of 2 or my tuple of 2, Python does the exact same operation. It goes to the slot number 2 and grabs whatever is there. One step done. There is no extra work for a list. There is no shortcut for a tuple. It's the same memory lookup either way. Think of like a bookshelf, whether the shelf is locked or unlocked. Finding book number 3 takes the same time. You just count to 3 and grab it. The lock does not help you find it faster. It just stops you for changing it. So the big tuple advantage is not in reading, it's in creating. We have seen tuples are faster to create. We have seen access speed is almost equal. Now, one more round of proof. And this one you can actually feel its scale. How much memory does each one eat? Before that, what is sys.get size of? Sys is Python's system module. It gives you information about what is happening inside Python itself. Memory, version, platform, all that stuff. Get size of is one function inside it. You pass any Python object to it, a list, a tuple, a string, anything, and it tells you how many bytes that object is taking up in memory right now. Nothing new here. We import sys, create a list and the tuple with the same 5 numbers, identical data, different containers. We call sys.getSizeOf of each one and print the result. That's it. 4 line total. Now let's run it and see what happened. 104 bytes for the list, 72 bytes for the tuple. Same 5 numbers, 32 bytes difference. That's roughly 30% more memory just to hold a list. This is where it gets really interesting. You might think both have 5 numbers, so they should be the same size, right? Wrong. And the reason tells you something deep about how lists are designed. A list in Python is built to grow. When you do mylist.append, Python needs space ready for that new item. But Python does not want to go hunting for memory every single time you append. That would be slow. So instead, Python is smart. When it creates a list, it secretly reserves extra empty slots. spare space, even if you have not put anything there yet. It's like moving into a new flat. You have 5 pieces of furniture, but you rent a flat with 8 rooms. Just in case you buy more stuff later, you are paying rent on 3 empty rooms. That spare space costs memory. That is where those extra 32 bytes are going. Empty reserved slots Python is keep reading for future items that might never even come. A tuple says, I know exactly what I have. I will never need more space. Give me only what I need and nothing else. No spare rooms, no wasted rents, 72 bytes.
Now we go deep. This is part most Python tutorials skip. We are going to use this module, short for disassembler. It lets us see what Python actually does when it runs your code. This is called bytecode instruction, the actual steps Python engine follows. Think of it like this. When you write Python code, Python translates it into a secret language before running it. This shows us that secret language. Okay, so what's happening here? Python says 123 list and does this. Creates an empty list, build underscore list 0, loads the constant values 1, 2, 3, extends the list with those values, list underscore extend, returns the result. That is 4 operation every time. Even if you write 123 list 1 million times in your code, Python does these 4 steps 1 million times. How tuples are made? 2 operations, just 2. Load constants. Hey, I already have this tuple pre-made and return value. Here you go. Python looks at 123 tuple and says these numbers can never change. So let me build this once, store it, and every time someone needs it, just hand them the same pre-built one. This is called constant folding. Python's optimizer is so smart that it builds constant tuples at compile time before your code even starts running. That is why tuples are 8x faster to create